function. In other words, if I'm at point A, which is right here, and I'm going to point B up there, if I take this path, I'm spending a different amount of way than going from A, going all the way up to the third floor, going down through the elevator, then going to B. So the weight depends on the path I take to go from A to B. While the internal energy, it doesn't matter. It only depends on UA, UB. The same for delta H for the heat. It doesn't matter for the enthalpy, how I'm going from A to B. But the work, it depends on the path. How much I put as a work, it depends whether I go straight from A to B or go all the way out all over this building to go to B. So the work is a non-state function, while delta H and delta U, the internal energy and enthalpy, is a state function. So the delta H, from now on, we're going to call it enthalpy of reaction. In other words, it is the heat. It is the amount of heat either released or consumed by a reaction. This is what is the enthalpy. Delta H, we call it enthalpy. Okay? Now, when we write delta H, we sometimes... Okay, let me insert... Okay. So delta H, this is the enthalpy. If you see delta H node, if you see that node there, that tells you that this heat, this amount of heat, this measurement is done at standard conditions, which is the pressure equal 1 bar and the temperature equal 25 degrees. So the reaction, they did this measurement at those conditions. So that small node in there that you see in table, that tells you that the experiment is done at 1 bar and as a pressure and 25 degrees Celsius as a temperature. Now, if you see R either after the delta or you see R in here, that means this is the delta H of the reaction. This R stands for the word reaction. Okay. And then you're asking yourself, okay, definitely it's going to be for the reaction. There is another delta H that we're going to learn about on Wednesday, and it's going to be delta HF0, and this stands for formation. And we're going to learn the difference between reaction and formation, the delta H formation and the delta H of the reaction. Now, as we learned before, delta H is a heat. So it is the amount of heat. If delta H is positive, we're still considering it the same as Q. So if Q is positive, is it an endothermic or exothermic? If Q is positive, endo or exo? It's endo. So the same for delta H. If delta H are 0, greater than 0, it's endothermic. If the enthalpy is less than 0, I mean by that less than 0 that it is negative, it has a negative sign, it is exothermic. So the same applies to delta H as any other Q. But we call it the enthalpy because it is for a reaction, not a process, not melting, not heating, not something like that. Okay, so let's learn about how we deal with this enthalpy, how we're going to calculate the enthalpy of some reactions. Now, let's start with this reaction, which is water gas. It's going to give me, it decomposes to give H2 plus half O2, and the delta H for this reaction as given is 241.8 kilojoule / mole reaction. So first of all, is this reaction endothermic or exothermic? The upper one, not the lower one. We're talking about the upper one. Is it endo or exo? Endothermic. So this delta H is telling you that this reaction needs heat to get going. For this decomposition to happen, you need heat. The second thing, when you see kilojoule per mole or joule per mole reaction, per mole and RXN, that tells you that this amount of heat is released for this reaction with this stoichiometric coefficient, with this exactly stoichiometric coefficient, 1 as a stoichiometric coefficient for water, 1 as a stoichiometric coefficient for hydrogen, and half for oxygen. In other words, if the stoichiometric coefficient it changes, that delta H wouldn't be the same. It will be affected. So when I say kilojoule per mole reaction, it is for the reaction as it is. In this case, the stoichiometric coefficient of the reactant is 1. In another reaction, you may find that the stoichiometric coefficient of the reactant is 2 or 3 or 5. It doesn't matter. Let's say 2A B plus 2C equal 200 kilojoule mole reaction. That's telling you that this reaction, when 2 moles of A reacts to give B plus 2C, this is how much is the amount of energy given. At least in this case, because it is positive, that means it's endothermic. Okay. Now, let's look to the reaction down there. So if you take a look at the reaction down there, it is the reverse of the upper reaction, of the reaction on the top. Look at it. The H2 plus half O2, which were the products, are now the reactants, and the reactant is a product. Now look at the delta H of this reaction, of the reverse reaction. It's exactly the same amount. It's 241.8 kilojoule per mole. The difference between the two is the sign. This one is endothermic, this one is exothermic. And this is a rule of thumb. The reverse reaction, any reaction, if you reverse it, the delta H is the same amount, but the sign is different. If this reaction is endothermic, its reverse is exothermic. If the reaction is exothermic, its reverse is going to be endothermic. But the amount of heat released or needed is the same. It's the same amount, 241.8. And this is the first rule when we're dealing with Hess's law. If I reverse a reaction, I'm only going to reverse the sign. Does that make sense? Okay, very good. Let's go to the next step, or to the next rule, second rule. Now, in this reaction, as I said a minute ago, that water needs 241.8 kilojoule per mole reaction for this reaction to happen. If we have 3 moles of water, how much is the delta H of the reaction? Okay, let's start with this. Would, for example, if I want to decompose 1 mole of water, do I need the same amount of energy to decompose 3 moles? Yes or no? No. Everybody agree? No. That's not right. It should depend. So everybody in the class decided or is sure that the amount that this delta H or the heat depends on the amount. If I'm heating 1 gallon of fuel, definitely it's going to give me different amount of heat than heating, for example, 1 gram or 1 liter of fuel. So definitely the heat, the delta H, the enthalpy depends on the amount. So how am I going to solve this? So it's going to start like this. I'm going to say, okay, in here it is given that there is 241.8 kilojoule released, given. For this case, it's given per 1 mole reaction. But for each 1 mole reaction, which is the one up there, I have 1 mole of water. And I kind of put the 1 mole of water because it's telling me what about the 3 moles. If it's asking about the oxygen, I would look to the stoichiometric coefficient of the oxygen. If it's asking me about, oh, what if you want to produce 6 moles of hydrogen, I will take hydrogen into consideration. 1 mole. So if I have 3 moles of water, how much is the energy? So let's see, the mole reaction gonna cancel mole reaction, mole water gonna cancel. So it's 3 times 241.8 kilojoule, and that's end up to 725.4 kilojoule. And I wouldn't put it mole reaction for this one. Why? Because now I'm talking about 3 moles. I'm not talking about the reaction as it is up there. Okay? So the second rule, the first rule, reverse the reaction, reverse the sign of the enthalpy of the reaction. The second rule, that the energy, the heat, or the enthalpy is amount dependent. It depends how much I have out there, how much I'm producing or is reacting. Okay, so let's start with an eye clicker. Let's see if you get the idea there. I'm going to stop it at 110. Okay. I'm going to stop it right here and check your answer. So I have C, and the most popular answer, C, is the right answer. So first of all, I have this reaction. I have 241.8 kilojoules per 1 mole reaction. And it's standing for each 1 mole reaction, I have 1 mole of water. Now here I don't have number of moles, I have mass. But we learned that we can calculate the number of moles by the mass over the molar mass. That's chapter 2. So what I'm going to do is 36 grams over the molar mass of water, which is 18.0 gram per 1 mole. So now I have number of moles right here. So 1 mole of water one more reaction gonna cancel, 1 more reaction, 1 more water definitely gonna cancel in here, and the answer equal 400.6 kilojoules. Okay? So this is again the same idea, which is that the amount of heat depends on, the heat depends on the amount. Okay. So I'm just gonna give it one couple of seconds because I see everybody is still writing. Okay. Now, so if you look to the 2 reactions up there, it's H2 gas, H2 plus half O2 is give you water. H2 gas plus half O2 is give you water. Yet if you look to the delta H, the delta H is different. Why would that be the case? If it is the same reaction, that means the same reactant and product, why is the delta H different? Yes, please? Very good. Excellent. That's exactly why the reason behind the difference. So the difference in here is not the reaction, it's not the reactant, it's not the product. The difference in here is the state, the phase that the product and the reactant are in. In this case, the product phase is different while the reactants have the same phase. So, and this difference is due that this one is in the gas phase and this one is in the liquid phase. And the difference between the 2 delta H's is the evaporation. the amount of heat you need to evaporate water or to condense water. It depends how you're looking at it. What does that mean? That means that the delta H depends on the state of the reactants and the products. So in other words, when you're looking in OWL, and that happens every semester, that you're working on OWL, you look to a reaction, and then you go to the tables to get the delta H, and you forget to look at the phase of the product and reactant. And you get frustrated because you look in the table, the delta H is that much, you go back to OWL, you're doing your calculation, and tell you you're wrong. And then you get frustrated. Okay, so make sure whenever you go to the tables on OWL that when you're looking to the delta H, you look at the delta H for the reaction that you really asked about. That means you have to look to the gas phase, to the state of the products and the reactants, because delta H depends on the state or the phase in which the reactants and the products are in. So this is kind of a summary. The independent of the path, the delta H is independent of the path. We talked about that, but we didn't see an example of that. We're going to see it in a minute. The second rule is depends on the state of the reactants and the products. The heat or the enthalpy depends on the state of the reactants and the product. And it depends on the amounts and how much moles or mass of the reactants or the products working on. The delta H, if delta H is less than 0, that's exothermic. If delta H is greater than 0, it's endothermic. So those are kind of the rules. Now we're going to use them to see how we can calculate the delta H of some compounds. In all of these, I gave you the delta H. I told you, oh, this reaction, this is how much is the delta H of this reaction. Now we're going to learn how to calculate this delta H. So let's do this one. This I can do before we go any further. I'm going to stop it at 2 minutes. Do you need more time, guys? So I'm going to stop it at 3. 100% for A. A is the right answer. Okay, so first of all, as we can see that the delta H is negative, so definitely it's not endothermic, it's exothermic. So C and D should not be your choice, even if you didn't do any calculation, should be direct. C and D are eliminated as choices. Now let's do the calculation. So it says that is this reaction endothermic? What is the enthalpy change if 1.25 gram of NO is completely converted completely to NO2? So I have a 114.1 minus kilojoule per 1 mole reaction. For each 1 mole reaction, I have 2 NO, not 1. Okay, so I have 2 moles of NO. Now I have the mass, so I'm gonna change it into moles, number of moles by dividing by the molar mass. So this is mainly the number of moles, the mass over the molar mass, which is the molar mass is given to you by 3.01 gram per mole. And the answer is gonna be minus 2.38 kilojoules. Okay? Okay. Now we're gonna move on to this thing. Okay. Let's say I have 3 reactions. Reaction 1, reaction 2, and reaction 3. A plus B to give C, let's say the delta H for this reaction, I'm going to call it delta H1, R. And for the second reaction, delta HR02, and the third reaction, delta H03. Okay? Now, what I can do for these reactions, and this is what state function means, I can add them together, I can reverse one of them, I can do whatever I want, I can multiply 1 by 2, I can divide 1 by 3, and whatever I do for this reaction, I'm going to do to the delta H. What does that mean? Let's say I wanted to multiply the first reaction by 2. So I multiply it by 2, and the delta H now going to be 2 delta H1. Okay? And let's say I want to divide, okay, I'm going to multiply the second by also 2. Okay? And then I decide, I'm going to tell you in a minute why I'm doing that and why we're adding it. Then I decide that I want to add those 3 reactions together. Now the 2C, when I'm adding this 2C in the product side, it's going to cancel the 2C in the reactant side of the other reaction, because now I'm adding these 3 reactions. This is how we can do that when we're dealing with these reactions. So the delta 2C going to cancel the 2C, the 2D now. What I have else? Okay, so then I have 2D and I have 1D in here. So let's start with 2A. So when I add it, I'm gonna have 2A plus 2B plus E. Then I'm gonna have Z plus 2F. And since I have 1D in here, if I take it to the other side, 2D minus 1D is gonna be 1D. Okay, everybody understand this? What I'm doing in here? It's really very important that you understand this step before suddenly you're gonna begin seeing chemicals. So I'm gonna repeat because I'm seeing some of you saying, no, we didn't get what you're doing. So first I have a reaction and I have a delta H for each reaction. Then I decided to multiply one of them by 2. Why I decided, we're gonna learn in a minute why I would do that. But the main idea that whatever I do to the reaction, I do to the delta H. So if I multiply the reaction by 2, I multiply the delta H by 2. If I divide by 2, the reaction by 2, I divide the delta H by 2. Now I'm going to add the 3 reactions after I modified them. I'm going to add them together. Okay? And when I add them together, if I have the same amount in the product side of one reaction and the reactant side of the other reaction, they cancel each other. This is maybe the first time you've seen this, that this is possible. So in other words, we're taking the chemical reaction as if they are equations, as if they are algebra or arithmetic equation, and the arrow is equal. This is what we're doing in here. And then 2A plus 2B, then I have the D in here, I have 1D in here and 2D in here. So if I take the D to the other side of the arrow, which is now an equal, it's gonna be D. Now what's gonna happen? What is the heat? What is the delta H for this reaction? It is the addition of all of these. So the heat of this reaction, or the enthalpy of this reaction, is 2 delta H1 plus 2 delta H2 plus delta H03. So all what I'm doing in here, that this reaction, I don't know the delta H of this reaction. So what I do, I use 3 other reactions, I modify them so that when I add them together, I end up with 2A plus 2B plus E, and I can figure out the delta H of that reaction. And this is Hess's law. This is what we're gonna do now. In a minute, the A and B and C gonna be chemicals. We have one reaction, which is the 2A, 2B plus E, that we don't know its delta H. What we're gonna do, we're gonna rearrange those reactions in a way that when we add them together, we end up with that reaction in here, and the delta H is the addition of all of those. Whether they are negative in sign or positive in sign, we add them together. Let's say this is minus 200, so it is in here minus 400, like 2 times minus 200. So if it is exothermic or endothermic, we take this into consideration. I think the most hard point for all of you is to understand, oh, she's canceling reactants with a product, and this is one of the ways, this is Hess's law, where we can treat a reaction as if it is more like an algebra or arithmetic kind of equation. And this is the hardest point. As long as you understand this, the coming 5 slides is going to be a piece of cake. Okay? Yes? Okay, so here's the question: can I take the 2b and put it to the other side minus 2b? You can do that, but that's in chemical reaction we don't have minus. This is why we try to keep, we don't have a minus 2b. That means it's a reactant. This is why we keep it on the right side. We keep everything as plus. We don't have minus. What does minus 2b mean in a reaction? It doesn't mean anything. And this is why I took the D to the other side instead of bringing the 2D to this side. Okay? So let's start with an example. Let's go a little bit higher. Okay, so the reaction that I don't know the delta H for is this one. It's the reaction of carbon plus hydrogen to give methane. This reaction happens in nature, yet it takes, for me to calculate the delta H, it needs 10,000 years for this reaction to happen. And just imagine I have to wait 10,000 years to calculate the delta H. I don't think I'll be there by that time as a scientist. So this is why we do this method. So to calculate the delta H for this reaction, what I'm going to do, I'm going to take those 3 reactions, which I bring these reactions and their delta H from a table. I'm going to rearrange those equations in such a way that when I add them together, I end up with this reaction. So the idea behind all of this is to get this reaction when I add those equations up. So the way to do that, this is the easiest way to do it. Begin with the first reactant. Say, I want the carbon to be solid and to be in the reactant side, and it should have 1 as a stoichiometric coefficient. So I would look to the equations. Which equation have carbon in the reactant and it have 1, this one, which is reaction 2. So what I'm going to do is the following. I'm going to name this reaction 1 or reaction A, reaction B, and reaction C. Okay? And then I'm gonna say, okay, this is the reaction where it has carbon, and this is the only place where carbon is there. So I'm gonna take reaction B and keep it as it is. I'm not gonna change anything about it. Why? Because I have the one carbon on the reactant side. And the delta H0 equal minus 393.5 kilojoule per mole. Now then I go to the next reactant, which is H2. I want two H2 and I want them in the reactant side. So I look to the three reactions that I have. The one in green, which is reaction A, is the only reaction that have H2 and it is in the reactant side. Yet it has one H2 and I want two H2. So what I'm gonna do, I'm gonna multiply reaction A by 2. Does everybody understand why I'm multiplying by 2? Okay, so multiply reaction A by 2. Then I would have 2H2 gas, 2 times half equal to 1. So now I end up 2 times half, 1 oxygen plus 2 water liquid. And since I multiplied the reaction by 2, I'm going to multiply this amount by 2. So now it is 2 times the 285.8 kilojoule per mole reaction. Now, I'm done from the reactant. I want the product. The product is methane, CH4. And CH4 should be in the product side and with a stoichiometric coefficient of 1. So I have reaction C that have methane, yet it have it in the reactant side. So what I'm gonna do? I'm gonna reverse the reaction. I'm gonna make the reactants the product's reactant. So reverse reaction C. And then I'm gonna end up with CO2 gas plus 2H2O liquid. That's gonna give me methane gas plus 2 oxygens, and since I reverse the reaction, it's exactly the same amount of heat, but instead of minus, it's gonna be plus. It's a plus, not minus anymore, because I reverse the reaction. Okay? I think I'm ready. So now what I'm gonna do, please everybody in this class, try to add those 3 reactions together. Go ahead, start. See, are we getting exactly the above reaction, this one? We don't want any element to be more or less in there. We need exactly the same reaction. Okay, so what I'm gonna do, I'm gonna start adding them up. The first thing, this CO2 in here, gonna cancel with this CO2 in here. The 2 water liquid in here, gonna cancel with the 2 water in here. I have 1 oxygen, 2 oxygen, and I have 2 oxygens in the other side. They're gonna cancel together. Yes, so when I add all these 3 reactions together, I'm gonna end up with this reaction. So if I add those 3 amounts as they are in here, I'm gonna get the delta H of this reaction. And I have to insert because I don't have enough room in there. So when I add those, it's gonna add up plus C carbon plus H2, 2H2 gas to give me methane. And the delta H for this reaction is minus 393.5 kilojoule, which is this one, plus 2 times minus 285.8 kilojoule plus 890.3 kilojoule. And the answer would be, for all of this, if you add them up, is minus 74.8 kilojoule per mole reaction. Okay? Get the idea? It's not straightforward. It's different of whatever you have learned in chemistry classes, okay? But the more you practice, the better you get in it, okay? So we're gonna start with an eye clicker. Let's check. And I'm gonna give you about 350, just because this is the first time you deal with Hess's law. And we call this Hess's law. Whatever we're doing right now is using Hess's law to calculate the delta H's. I encourage everybody to try and do this while in here before you go to OWL and get frustrated. Okay, so I'm going to stop it right here and check the most popular answer. And I have A to be the most popular answer. A is the right answer. Okay, I'm going to insert. So I have methane plus half oxygen to give me methanol. So the first thing, I want this reactant to be in the reactant side with stoichiometric coefficient 1. So I'm going to call this as reaction A and reaction B. So I'm going to keep reaction A as it is. As it is. So it's methane gas plus 2O2 gas to give me CO2 gas plus 2H2O and minus 8O2.4 kilojoule more reaction. Now, then I look to half oxygen, and I look to the two reactions, and the two reactions, they have oxygen in there. So what I'm gonna do, the easiest way to handle it is skip it. Skip it and go to the other reactant on our product, and once you balance those in the reaction, you're gonna end up the oxygen canceling each other. And this is usually happens whenever you have your reactant in two reactions or more. So I'm gonna skip the oxygen, go to the methanol. I want the methanol to be in the react product side, and I want it to have stoichiometric coefficient of 1. So all what I have to do is to reverse reaction B. Reverse B. So now I have CO2 gas plus 2H2O, giving me 3/2 oxygen gas plus methanol. And then definitely this line is going to be plus. Why? Because I reversed the reaction. Now I'm going to add the two reactions together. And clearly the CO2 going to cancel, the water going to cancel. Now, usually, so I have 2 oxygen in this side. And on the other side of the equation, I have 3/2 oxygen. So 2 minus 3/2 oxygen, it's 4 minus 3/2 equal half oxygen. If you forget how to handle fractions or how to handle this kind of subtraction, please go back and do a revision, because this is the major problem each time we get to Hess's law, that some of you can't do this calculation. 2 minus 3/2, they can see that it ends up to half. So this and this gonna end up to half oxygen, which is exactly I want in here. So that implies I have to add those two numbers to get, and the answer is, if I add those two numbers, 126 kilojoule more reaction, and this is the delta H of the above reaction. Okay, let's do some more on this. I'm gonna stop it at 3 minutes. Okay, I'm gonna give a couple of seconds more just because I know there is 100 something. Okay. Send your answer. I'll stop it right here and check what you. So I have the 39%. It's not a very high percentage yet. It is the right answer. So B is the right answer. Now how come? Let's do that. So I'm gonna again name it as reaction A, reaction A, reaction B, and reaction C. And I encourage everybody here just to concentrate what is going on in here, because this is kind of a very common example that you're gonna see often. Okay. First of all, half and 2. So it's clearly that I'm gonna divide the reaction A by 2 or multiply it by half. So multiply reaction A by half or divide it by 2. So I'm gonna have half and 2 plus 3 over 2 H2 gas and H3 gas and minus 9 over 1/8 over 2 kilojoule per mole. Yeah. Now, oxygen, it is in 2 reactions. I'm going to skip it. It's going to balance itself as we go. NO, I need NO, and it is in the product side and with a coefficient of 1. So I see that there is an O in the product side, but it has coefficient of 4. So I'm going to divide reaction B by 4 or multiply it by 1 over 4. So multiply reaction B by 1 over 4. So I'm going to end up with ammonia gas 5 over 4 oxygen, NO 1 plus 6 over 4 water, and the number in here 906.2 over 4. Okay, now you think, okay, let's add those 2 reactions. And if you add those 2 reactions together, you're gonna cancel the ammonia, yet you have 3 over 2 water, or 6 over 4 water there, which is 6 over 4. They're going to cancel to 3 over 2. So, no, you have to cancel the water. It's not that obvious as you begin there, because you think, oh, if I add those 2 reactions, I may end up with the above reaction. Yet this is not the case. It's not going to end up with the above reaction because you're going to have water. So what I'm going to need now, I need to cancel this 3 over 2 water. So in other words, I need water to be in the reactant side, and it should have a 3 over 2. So I look to here, and I find water, but it's in the product side, not in the reactant side, and it doesn't have a 3 over 2. So what I'm going to do is reverse C and multiply it by 3 over 2. So reverse C and multiply it by 3 over 2. Now, if you do so, you're going to end up with 3 over 2 water gas to give 3 over 2 H2 gas plus 3 over 4 oxygen. So I'm going to put plus 2 for 1.8 and I'm going to multiply it by 3 over 2. Now, if you add the 3 reactions, you're going to get the above reaction, which is half N2 plus half O2 to give NO. That means if you add those numbers,